Our next speaker, coming from out there, is Cynthia.
Okay.
I guess it shouldn't take more time. Please go ahead.
Okay, thank you very much. Toni, happy birthday. And I'm absolutely delighted to be part of this and honored to be so early in the schedule. So this talk is going to be as narrow as Russell's talk was broad. And I'll just start. So in case you don't know, differential privacy is a definition of privacy tailored to the statistical analysis of large data sets. And it says, roughly speaking, that the outcome of any analysis is essentially equally likely independent of whether any individual joins or refrains from joining the data set. And there's an equation that captures this, which is that if we have two data sets, X and Y, that differ in the data of just one person, and we have a mechanism M that is going to give us differential privacy with parameter epsilon, then for any possible event S, the probability that we observe S when the database is X is at most e to the epsilon times the probability that we observe S when the data set is Y. Okay. So most of the work on differential privacy for a long time was in the setting in which there was a static data set and all of the data were collected in one place, and there was a curator who runs the algorithms and does all the right randomness and releases results. And together with Toni, we started looking at the case of dynamic data. This was about 2008, 2009, and papers came out about a year later. And there were sort of three issues that would come up alone or in combination. So here I have pictured a data stream. You can think of a data stream in which data of an individual can appear multiple times. For example, we might have a stream of search queries and I might make 2 or 3 searches. Or maybe a stream of movies watched on Netflix by different people, and a given individual might appear multiple times. Maybe the yellow user here watched 3 movies in this snippet. And in user level privacy, we want to protect all instances simultaneously of a user's participation, like all movie watching by this person. And in what we call event level privacy, we want just to protect the privacy of any individual event. So in other words, with user level privacy, we would be protecting your sustained love of Mickey Mouse movies, versus in event level privacy, we would be protecting the fact that you viewed one Mickey Mouse movie last night. So that was the first issue. The second issue had to do with trying to prevent mission creep with data and protect against warrants and subpoenas. So we introduced a notion called pan-privacy, where what we want to keep, we want privacy over the joint distribution, not just on the outputs that are produced by the algorithm, but also on the algorithm's internal state. So the algorithm maybe has some data, it does an analysis, it releases a result, and then somebody gets a warrant and goes in and looks at the internal state of the algorithm. So we want to be sure that the internal state isn't revealing information about individuals, even in conjunction with what was produced as outputs. And okay, and the third issue is what we call continual observation. So we might be doing something with longitudinal data, which can change during every time period. For example, we might be continually reporting things like users who viewed this item also liked some other item. And this was a real example that happened with a very generic sort of first item. So it was really interesting who actually looked at that first item in the story of, oh. Anyway, or daily report of the number of tests or COVID cases by county, or maybe cholera cases by individual wells, or total number of app downloads during some time periods 1 through T. So this is now the algorithm is continually reporting sort of cumulatively what has happened. which is more challenging than just doing some processing and outputting one single output. Okay, so I want to focus first on continual observation. Maybe this is a variant of Russell's question, how many of us are present versus how many of us have shown up. So I want the approximate total count, i.e. prefix sum, at every time step, how many people have shown up so far. So one thing that we could do, let's assume just for simplicity that at each step only 0 or 1 people show up, just for this particular slide and this point. We could use, say, randomized response or Laplace noise at each step. And if we do that and we run for some capital T number of steps, the error will look something like square root of T over epsilon, where epsilon's our privacy parameter. But instead, it's natural to use a tree-based counter, which gives us event-level privacy. So I'm focusing on event-level privacy. And I'm going to be sort of pounding on this one particular story, but there is, or example, but there is a serious payoff that comes at the end. So here we have a non-private tree-based counter. You could, it's a complete binary tree, and the nodes are labeled starting at 0 and ending up at T in binary.
Can I interrupt with a question?
Yes, T minus 1.
So in your picture, you had like things marked yellow and blue, and I said there are different events.
Yeah, so in the yellow cell, sorry, in the yellow cells, somebody showed up, let's say, and in the green cells, time periods, nobody showed up.
Oh, okay. But so you're looking at like event level. Are the different kinds of events, what counts as an event, what are related? Is that known to the algorithm? Or
Yes.
do we have to worry about arbitrary?
No, these are very specific kinds of events that you're counting. Like, again, how many people tested positive for COVID today?
Okay, thanks.
Okay, so good. So a non-private tree-based counter, you could imagine something like this. I've got some power of 2, and I'm labeling the nodes, the leads from 0 to 2 to the T minus 1. And we could put the data at the leads, and we could put the subtree count at the internal nodes. And certainly from something like this, it's very easy to figure out for any prefix, how many people, what the prefix sums are. So for a prefix of length little t less than t, write little t in binary and follow the following algorithm. I'm writing t in binary as b1, b2 up to b log t. So if bi is equal to 0, we just move left and do nothing. So here in my example, t is 3, and I want the sum of the first 3. So this is 0, 1, 1. I move left because it's a 0. But I don't do anything. And then if the next bit is a 1, I'm going to move right, and I'm going to add the prefix sum at the left child of the node before I make that move. And then there's another 1, so I do exactly the same thing, and that gives me the count in the first 3 cells, the sum of those 2 guys, okay? And special case for the root, if I want all capital T, I have to read from the root. So not complicated, tree-based counter. And of course, all of my prefix sums are now expressed by the sum of at most log of capital T number of values. The differentially private tree-based counter looks very similar, only I have noisy counts, noisy data at the leaves and a noisy internal nodes. And the noise is drawn from the Laplace distribution with parameter 1 plus log T, capturing the fact that an individual can affect the data at 1 plus log of T many nodes. Okay. Good. It's a variant on this. It's a differentially, again, a differentially private tree-based counter, but I'm not going to be storing a lot of stuff internally. I'm going to just publish prefixes as I get them and allow users to take published data and put stuff together. So all I need to do is say, what do I need to publish? So initially, I'm going to initialize all of the nodes internally, all of the nodes, sorry, in the tree with independent noise, independent draws from this Laplace distribution. And I'm going to initialize the count to 0. And at each time step t, I will add to the count x sub t minus 1, because remember, I've named these guys. This is the first guy, but it's labeled t minus 1. It's labeled 0. Okay. And then I output, when I want to output, say, this thing, I output the value, the count so far, plus the sum of the noises that I created at all of these levels. So mathematically, it's very similar to what we did before. But it's not going to be pan-private. So the first thing we want to do is we're going to shrink it. So this is small continual output, differentially private tree-based counter. And the idea here is just like before, only when we've completed a subtree, we just prune it. We get it, we delete it from memory. And we don't create nodes in this tree until we actually need them. So functionally they work as before, but we don't create, we only keep a sort of a log-sized object working at any time. And it turns out that this is pan-private. So not only is it differentially private under continual observation, but because of the way we've handled the noise, it's also pan-private. If somebody were able to break in and see what's going on in the internal nodes, even then privacy would be maintained. Okay, now, we don't actually need pan-privacy for the rest of this talk, although I'll mention it once more at the end. But we're going to be interested in this algorithm, again, because it has this special property that I'm writing here in blue, that all of the outputs are sort of the true counts at this time, plus the sum of 1 plus log of t, identically distributed random variables. So one of the things that we did in this paper was we said, we're going to give you an example of doing something non-trivial with a counter or with prefix sums. So we looked at the online learning algorithm of Follow the Perturbed Leader by Toniann and Dhampala. I think it's 2005. And what we want to do is we wanted to keep private the experts' recommendations at any individual step. So, the intuition, so this is the original algorithm, the non-private algorithm. We have some k number of experts. For each expert, we choose a weight at time t with according to an exponential distribution, and then letting c sub t at I denote the total cost or regret sort of so far for that one particular expert. We compute the cost minus this perturbed random value, and we choose the argmin I of this difference. Okay, so that's the Toniann-Dhampala algorithm. Now, what we did was we sort of observed that the only thing that mattered was the total cost so far for this particular expert. So for each expert, we only need its total cost so far. So we said, okay, let's maintain an approximate cost so far using this differentially private under continual observation tree output algorithm. Now, we know that the quality of our outputs are going to be pretty good. That is, the differentially private approximation is going to be pretty close to the truth. But we actually we don't know, maybe somebody else knows by now, but we certainly didn't know how to argue success for our algorithm based solely on the approximation error. However, fix a particular expert and let y sub t be the cost incurred by this expert at time t, plus the noise that we would get in the approximation, plus any of the randomness in the follow the perturbed leader algorithm. That is in particular here in step 1 of that algorithm. So remember, at each step, the noise in the approximation is the sum of 1 plus log of t independent draws from the Laplace distribution. So we're using this property now. The expected sum over t of yt, so the expected cumulative cost is the sum of the expected costs for this particular expert, which in expectation is the same as what we would have gotten if we did our 1 plus log t draws from the Laplace, added them all together, called that our 1 round noise, and added the same 1 round noise at every step. This is just a thought experiment. We're not saying to do this, but it's a thought experiment. In expectation, these would be the same. So we would be looking at the sum over t of the expected value over a particular one set of 1 plus log t independent draws from the Laplace of, well, the red stuff is the red stuff. So now we have the cost incurred at t plus the randomness of this plus that red stuff. Okay. Now, just like an insight into where we're going, we can view this sort of fixed noise as an extra cost that happens in some prefix. It's not changing round to round. So it's as if we had been running the follow the perturbed leader algorithm and incurred some extra cost in some prefix. And now we can kind of use the power of the Kalayan-Dhampala argument to argue that the overall regret is small. Okay, so we started with these definitions of privacy and privacy in the online case. And then we noticed that some learning algorithms really only depend on cumulative loss. I mean, they all do, but cumulative loss. And we did something sort of useful with that. So that notion was picked up on, I think for the first time in 2013 by Smith and Porta. And they applied it to online convex optimization. But, and I'll get to that in a minute, but let's back up for a second. Remember just your standard online stochastic gradient descent. So you have as inputs to the algorithm, this is not private, just the usual stochastic gradient descent. We have a convex set C in p-dimensional space. We have some step sizes, A to 1, A to 2, and for the rest of this thing, I'll just make them all the same. And some initial point x naught in C. And in iteration T, we let xt plus 1 be xt minus the learning rate times the gradient of ft at xt, and we project all of that down to C. So, and I'm going to call this gradient GT. So GT is typically a loss that you would say incur if you get a new data point d sub t plus 1, and we're at location xt. Okay, did I say that? I meant GT is the gradient of that. FT is that loss. Okay, so that's just standard online stochastic gradient descent. Now, prefix sums can play an important role, and they've turned out to be playing an important role in online convex optimization and private gradient descent, and in gradient descent in general. But the point is, if you want to do your online learning with privacy, you would want a differentially private version. So just as follow the perturbed leader only cared about the cumulative costs incurred by the experts, online convex optimization and stochastic gradient descent only care about cumulative sums of gradients. So you can see this by and this inset comes from Amardeep Thakurta, you can deconstruct the SGD model update. So theta t plus 1, what I was calling xt plus 1 in the previous slide, is theta t minus the learning rate times the gradient at time t. And that, just by expanding theta t, is theta t minus 1 minus blah, 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 which turns out to be, when you unwind it all the way, your starting point minus the learning rate times the sum of the gradients at all of the steps. So the insight that Adam and Amardeep had in 2013, so 10 years ago, was, gee, we should keep track of these cumulative gradient sums, prefix sums, using the tree-based method. And it turns out that not only does that work for stochastic gradient descent, it works for also online convex optimization, and in particular, follow the regularized leader updates. And so what that tells us is that this differentially private method for keeping prefix sums is very useful for differentially private learning. And that has suddenly become of very, very wide interest as industry kind of moves whole hog into trying to do AI and machine learning, but in particular, trying to add some privacy. So there are a number of options when you want to try to get some kind of privacy preserving stochastic gradient descent. You could do something very naive, which is perturbation, say using the Gauss or some other method at each step for the gradients themselves. And that's very expensive computationally and doesn't give you the best bounds. Then you could do a really cool trick that Vasily Smith and Thakurta came up with, which is randomly sample 1 point and blow the effects of this 1 point up by the size of your data set, and trade off the privacy loss that you get by what's called privacy amplification by subsampling with the cost of increased sensitivity that comes from blowing things up. So that's a computational improvement, but not an improvement on the privacy. Then there are mini batch algorithms where the privacy comes in part from subsampling, from the privacy of the subsample at every step. Then because there are some concerns about how do you do this uniform subsampling and how do you keep private in a really large system where you can't keep secret the fact that data are moving around. How would you have privacy of the subsample? So there's a whole notion of what's called the shuffle model, which is a different form of computing. There are techniques called amplification via iteration that sort of say, hey, we don't need every step to be differentially private, in the sense that we don't need to see the outcome of every step. We can hide the journey. All we care about is where we get at the end of the learning process. And if I understood the literature, there are some similar issues about that the mini batch model has, at least according to a paper by Kairouz et al. And then there are the prefix sums of the gradients, which then will avoid a lot of these, which seem to avoid these issues. So last year, Google announced that in the Gboard for European Spanish next word prediction, they trained a production model using this private tree. And here's what they said about it. This is the first production neural network trained directly on user data that has this formal differentially private guarantee. And we don't have time to go into it, but it satisfies some form of zero concentrated differential privacy. So in my last slide, the paper on pan privacy has several proofs, several lower bound proofs and impossibility results. And today's question is, where did Toni write one of these lower bound proofs? So I'm going to say that she wrote it on 101, which is true. She wasn't in a building near Route 101. She was actually on Route 101, and she was driving at the time. And that's my embarrassing story about Toni. So Toni, thank you so much. Here are some of the things that we did together. We did privacy under continual observation. We wrote the Fairness Through Awareness paper together with Rich and others, which sort of launched the theoretical study of algorithmic fairness. We did work on learning fair representations, which has taken on its own life. And we worked together on showing that differential privacy and some other techniques that leak little information protect analyses against data dredging and data exploration issues. So thank you, Toni, for your brilliance, for your work, for your collaboration, and for being my very dear friend.
Thank you so much, Cynthia. It's amazing to see the variety of things that Toni done. You're amazing, Toni, but you know. Any questions, any comments? You could speak up, those microphones should pick it up, or I could give you the mic. And if people are online, you're welcome to speak up as well.
Thank you, Cynthia. It was a great talk.
Thanks for the opportunity.
No, I don't have any questions. Well, I'll ask these few later, but yeah, thanks for a great talk. I don't know how many people understood it, but I thought it was really clear.
Yeah, thank you so much. It's such a cool stuff. Okay, if there are no more questions, and you're welcome to log into Zoom and ask questions. Thank you very, very much for coming. And we have a 25 minutes break till 11:30, and then we'll reconvene here for even more talks from even more parts of Toni's work. And thank you so much, Cynthia. It's an honor to have you.